flanged square end duct?
Yeah.
Okay, good. Let me see if I can't draw that. Okay.
Page 16?
Chart 16.
Chart 16.
No, chart 13, page 16.
I don't have page 16.
Chart 11.
I do not.
Maybe yours got mixed up with here. Here you go. Here's the second copy of it. Here, copy of it, and is that 16? What is this? There's another 16.
I don't think there is.
Yeah, no.
Okay.
Okay. Here's 18. Here's 19. That's 14. Okay. Okay, yeah, there is no 17. There is no 17. Okay, so there's our flange duct. Not very pretty. But we're going to have round duct coming off of this, right? And a round duct coming off of this. I'm going to have an elbow. And it's going to turn and go in the direction of where the exhaust is going to be for the rest of the system. So this is a flange duct. Flanged square. Okay, so now, what quantity of air am I going to have to pull through this duct? How many cubic feet per minute? Well, first I need to know what is it I'm trying to do. What am I protecting the worker from? If you go to, let's see, chart number 9, I think it is, which should be right behind your hood charts. There's different materials. Okay, different particle sizes, grain, wood dust, sander dust, silica dust, so on and so forth. Like silica is very high, a lot of feet per minute that you need, and so on and so forth. A lot of the transport velocity is very high. So now let's say that first thing, before we worry about transport velocity, we want to know what distance is the worker going to be working from this flanged hood. Pick a distance. Let's make it a foot. 6 inches, 60. I have to be right up against it. Let's make it a foot. Okay, so the distance is 1 foot. That's our x, right? So if I look at the formula here, right, I'm going to use the bottom formula. I know what x is. What's the area of the flanged hood? How big is this flanged hood?
8 by 12.
8 by 12, 8 inches by 12 inches. Okay, so 8. That's 2/3 of a foot by 1 foot. So it's 0.67 square feet, right? So the area is 0.67 square feet. X squared is 1 foot times squared, which is 1. So this is 0.75 times 10 plus A, right, is what we want coming through this thing. Okay, so what does that work out? Times the capture velocity. Now imagine, what is this guy working with, do you think? You think he's working with some fumes? How about just some fumes? We won't even worry about particles for now. Okay, so fumes, typically, 200 is a lot. 200 is what you have at the face of a lab hood. That's a lot of velocity. Let's be a little bit more conservative. Say 100 feet per minute is enough to pull these vapors away from him. 100 feet per minute is quite a bit. You'll feel the breeze on your hands at 100 feet per minute. If you have a lab hood, usually you're raising the curtain on the lab hood to a level that's like, say, we give you either 100 feet per minute if it's a not very hazardous material, or 200 feet per minute if it's really hazardous stuff and you really want to make sure that you capture the stuff. So let's use 100 feet per minute, 1 foot away. So what is Q? What volume of air do I have to get for this duct that we just designed? So it's 8 inches by 12 inches. In other words, 0.67 by 1 foot. Okay, so what does Q got to be equal to? Anybody figure it out yet? It's 0.75 times 10 squared, 10x squared, plus 0.67 square feet times the capture velocity, which is 100. Okay, so that's equal to 0.75 times 10.67 times 100. Right, 0.67 plus 10x squared.
X is 1 foot.
Yeah, 1 foot. Right, so x squared is 1.
Oh, I'm sorry.
Times 10. Right, times 10 is 10.
Yep.
Plus 0.67. So this is, multiply this by 100. We move this over 2 places. So it's 0.75 times 1,067. What does that come out to be? 0.75 times 1,067. That comes out to be 800 feet per minute, 800 cubic feet per minute.
So the question,
Yes.
if you did your math like that, and you come up with something like 1507.
Yeah.
Can you just round it off to 1500?
I would keep, I like to keep the numbers the way you get them
Okay,
until the very end,
okay.
and then round at the very end. The reason why I'm used to doing that in statistics, because in statistics, a lot of times what you're doing is you're taking the square, you find a value, then you square it, and then you multiply it by something else. So what happens every time you do an operation with it, you multiply the error, right? So I would keep as much as I can. I'm going to say it was really 800 point something or other, 800 point, I lost it there, 0.25. 800 is good enough for our purposes. Remember, these are really this is really an estimate of what we really need to do this. There's a lot of other factors that are going to wind up in here, kind of like making this maybe not work so well for us. Okay, so I think this is galvanized iron ductwork, right? That's round ductwork. That's usually what I would expect to see in a system like this. And we have one elbow here. What kind of elbow do you think we have here? 3-piece, 4-piece, 5-piece? 4-piece. Okay, 4-piece elbow, and it's a 90-degree turn, right? Looks like a 90-degree turn to me. All right, so now I got another hood over here. What kind of hood should we have here? Pick something else out, something interesting. Yeah, don't go for these simple hoods. Give me something interesting. How about the slotted hood with 2 sides and a back? Okay, you see that one on page 18? Yep, page 18, slotted hood with sides. It's the second one down.
Oh, yeah.
Slotted hood with sides and back. All right, now let's see. Okay, so that looks something like, let me see if I can't butcher this drawing. Okay, that's going to look something like that and like that. We got a table coming out in front of it. And we have sides, look something like this. And we got a slot at the back of it. I'm going to say that this is 4 feet wide, and it's got a 1-inch slot at the back of it. And let's see, what is the value that we're going to need here? How much? What quantity? I'm going to say that he's working on his table, and that he's working with a particle. Let's say the particle he's working with is, where'd my 9 go? Give me a small particle, something not too big. How about, well, we use the thing at the top here, a fine dust of powder. So we want 3,000 feet per minute of capture velocity. But on the table itself, we're going to need, we're going to want some capture velocity on the, that's transport velocity on this chart. But on the table, we're going to determine some capture velocity. Maybe we want that to be 200 feet per minute. Okay, a little bit faster than we had before. So now we have to figure out what quantity of air that we need. Well, how do we figure that out? It's equal to 0.05 times pi. It's equal to 0.05 times 3.14 times the length of the slot, right? The length of the slot is 4 feet, we said, times the capture velocity that we want, okay, which is 200. Okay, now in this particular hood, they make a note of the fact that the slot velocity, the face velocity at the slot is going to be somewhere between 100 and 150, 1,500 and 2,000 feet per minute. Okay, so we're, and let's see, BC. Okay, so now there's 2 versions of this. One version of this has a straight takeoff. The other version of it has a tapered takeoff duct. So in other words, that at the back of this thing, there may be some sort of tapered device that tapers into a round duct, which then goes up here. We'll use the tapered version of it. For the tapered version of it, the K value that they give, K is equal to 1.78, right? What was K for our flanged hood?
0.70.
0.70, okay. Okay, so for this one, it's 1.78. So now the amount of air that we're going to move here is going to be 0.05 times 3. I think VC is going to be the velocity at the slot, which is 1500. I think that's why they're giving us the slot velocity. They're giving us the length. They're not telling us the size of the slot. Oh no, we have a distance x. Okay, so we're gonna assume that this table is 2 feet wide, and that we want to have 200 feet per minute 2 feet away from this. Okay, and I left that out of this formula, didn't I? Pi times 3.14 times 2. Yeah, I'll put it over here. Times the length of the slot is 4 times 200 feet per minute is what we want going across 2 feet away from that slot. So what does that Q come out to be? Comes out to be 800, 1600, 1600 times 3.14 is equal to 5,024 times 0.05. And I get 251 cubic feet per minute. Does that look right to you guys? Yeah. 800, 1600 times pi is about 5,000 times 0.05 is about 250. So Q is 250 feet per minute. Cubic feet per minute. Cubic feet per minute. Okay, so we got Q for this duct, Q for this duct. Now we have a duct going up here, and now we want it to join the main duct. So we are going to have a junction, or a T, that's going to look something like this. It's going to start out narrow. It's going to get a little wider because we have additional air that's going to join this. And this junction is going to have a specific angle. What angle should we give the junction? Smaller, okay, let's give it 30 degrees. The smaller that junction, right, smaller the angle, the more it's moving in that direction anyway. But in order to get there, we got another elbow over here. Okay, and we're going to use the same kind of elbows throughout. 4-piece, 90 degree. Okay, now we have this duct. This new duct, the main duct, is going to continue along to an air filter. Okay, well, now we got a problem here. We have a fume here, and we have a particle here. So we're going to need some sort of filter that has two media in it. It's got a media filter, and it's got an activated charcoal filter, right? And then from there, we're going to go to the fan. And from the fan, we're going to go, let's say the fan, well, I'll tell you what. Let's go here. Let's say that we have to turn to the right and then turn back to the left. And then we go to the fan, and the fan goes up through the roof 10 feet. Okay, so the distance between, I'm going to call this hood A, and I'm going to call the junction B. I'm going to call this hood C, and I'm going to call the junction, I'm going to call this hood B, and I'm going to call the junction C. So the distance from A to C in terms of the amount of ductwork, I'm going to say that that's 50 feet of ductwork. The distance between, and there's one elbow, the distance between this slot hood and the junction, I'm going to say is shorter, it's 30 feet. Okay, it's also galvanized iron. It's 30 feet and it's a 30-degree angle on the junction. And then the distance from C to the fan, I'm going to call the fan D. It's going to be, I'm going to say that that's another 50 feet. And then we have one elbow, a second elbow, and then we're going to go into the fan suction. So we have two elbows, but the amount of ductwork we have here is say 20 feet. And then the stack is 10 feet tall coming off the fan. So altogether, we got like 50, 100, 130, 150, 160 feet of ductwork altogether to account for. Okay, so now let's start designing this system on our spreadsheet. Okay, so now I gotta get my spreadsheets. Okay, and I'm going to the student materials. Get my spreadsheets. He really doesn't give you a blank one to start out with, unfortunately, which I'm not sure why he does that. Let's see, industrial ventilation spreadsheets, US units. Okay, whoops. I think this might be the one I want. Yes. Well, you've got to do a little bit of research. In other words, the reason on the vapor, my reasoning there was that a standard lab hood usually has a face velocity of either 100 feet per minute for something that's not terribly hazardous. You know what I mean by the face velocity, the average velocity across the opening of that hood, 100 feet per minute. Or if it's something really hazardous, 200 feet per minute. So I'm saying that this is not something all that hazardous. So I'm saying where he's working, a foot away from this hood, where he's handling these solvents or whatever he's doing, or painting, or doing some other, spray painting, or do some other activity, that I want 100 feet per minute velocity, pulling that away from him. If it's a really hazardous material, I might want a higher velocity than that. Okay, on that slot hood, I was saying he's working with some sort of particulate, right? And a particulate is going to be a little bit harder to pull away than a fume is, right? Because you have to carry it in the air. I call that 200 feet per minute across from the furthest point. That was 2 feet to the end of that table. In other words, at the end of that table, I had 200 feet per minute. Yes. Oh, no, when we're working with a lab hood, you're putting your hands inside the hood, right? So a laboratory hood is different. But this, I'm just giving that as an example of what kind of velocity I might want as a capture velocity. Okay, but you might want to research it, like in other words, see how hazardous material, see if somebody else recommends what the velocity you might want. But it's going to depend, it's going to be very specific to the material that you're working with. Yeah, absolutely. So they're going to be a lot more. In other words, 100 feet per minute on that hood is that if you look at the head, if that hood goes up like 2 feet and it's 6 feet wide, that's 12 square feet times 200 feet per minute or 100 feet per minute. So you're going to have your Q is going to be a lot larger than this. Yeah. Initially, I was doing 300, but too much. Well, think about it, 300 feet per minute. Yeah, convert 300 feet per minute to miles per hour. And then think about how fast that is. And if you're trying to work on something delicate, you also don't want like, yeah, exactly. You have to make a judgment, as to like, how you have to work practically too. Okay, 100 feet per minute, 200 feet per minute, I don't think you'd feel it, right? You'd feel it, but I don't think it would interfere with most kinds of work that you might be doing. Okay, so at any rate, so let's see if we don't have all I want the one with the 4 tables, with the multiple tables on it already. Make up airflow, duct design, expanded, that's it. It's called duct design expanded. Okay, so I'm gonna blow this up real big so we can all see it. Okay. Okay, now there's actually 3 spreadsheets on this duct design chart 12B expanded that's in your text. There's actually a number, there's this first pair of columns on this first sheet workbook. There's a second workbook and there's a third workbook. Okay, you kind of set it up so that there's even a 4th workbook, it looks like. Okay, well, yes, as a matter of fact, sheet 1 of 4, 1 of 4, 2 of 4, 3 of 4, and so on and so forth. And we'll see why he's got multiple of them. Okay, so now, first thing I'm going to do is notice that it's read-only. If you look way at the top there, it says read-only. It's protected, so you can't erase this or change it, right? So I'm going to go into Tools. I'm going to say Protection, Unprotect the Sheet, right? And his password is Jeff, Jeff. Okay, I don't think the case matters. Now it's unprotected. I can start making changes. If I save this now, it probably, if I try and save it, it's going to warn me not to overwrite the original file. But to make sure I don't do it anyway, I'm going to say save as, and I'm going to save this as class duct design. I'm going to put it on the desktop. So now I'm working with a whole new file that like I save separately, and I can make changes to without worrying about the original. So, okay, first thing I'm going to do, I'm going to go up to the first spreadsheet, and it says start here. Okay, this area over here, it says if coming from a junction, fill this stuff out. We're not coming from a junction yet, right? We're coming from the first hood. Okay, we're going to start here. And this first column is going to represent the run from A to C. That first hood to the junction. A is the first hood, C is the junction. Okay, and first thing I got to tell it is it uses this as triggers to tell it what formulas to use. Where am I coming from? Well, if you're coming from a hood, you put 1 here. If you're coming from a junction, you put 2. Since we're coming from a hood, we're going to put 1 there. If you're going to a fan, if it's a 1 hood system, we're going to be going to a fan. Everything's going to be done in this and the next column because we're going to the suction side of the fan if it's a 1 hood system right away. And then the second column would be just the continuation from the suction of the fan up the stack. Okay, if we're going directly to the fan, we put 1 in here. If we're going to a junction, we put 2. So we're going to put 2, going to a junction. Okay, so now I have to tell it for going from A to C. Okay, what Q do I need? What did we say it was going to be? Remember, 800, right? Okay, good. Okay, how many feet of ductwork do we have between A and C? How much? 50 feet. Good memory. Okay, 50. What's the velocity, the transport velocity that we need for this material? Now, we said it was a fume, right? I'm going to say for a fume, 2,000 is enough. Okay? Because I think most of the stuff that's in that chart is really for particles. But for a fume, you can imagine it's not going to drop out onto the bottom of the duct like a particle. So I'm going to say, I can be conservative and say 2,000. I don't need a whole lot. Okay, so now what is R for the type of ductwork that we're using? Galvanized iron ductwork is 1. If we use flex duct, we look it up on which chart is that? Is that 10 or something like that? That is chart 10 is roughness, right? So if we were using riveted steel at 2,000, it'd be around 2 or 2.1. If we were using, let's see, flex duct at 2,000 feet per minute, it'd be 2.6 would be the roughness factor. But for galvanized iron, that number is 1. Okay, and next thing is, if there's a slot in it, how long is the slot? You remember how long was that table? Remember slots at the back of the table. Table was 4 feet wide. I'll bring it up front here. Yeah. Oh, I'm sorry. Oh, I'm losing myself here. You're absolutely right. There is no slot there, right? So we put 0 there. See, right next to it, it says plans, no slot equals 0. And the slot velocity in feet per minute is 0 since there's no slot. Okay, so now, next, in this point now, if we're coming from a junction, there's no hood. If there is no hood, we put a 0. If there is a hood, we put a 1. So we put a 1 there. Okay, so now, next thing we need to know is, next thing is the acceleration. That 1 is the acceleration factor. If you have a hood, you put a 1 there. That's to indicate to it that you're starting from still air and pulling still air and getting it in motion. The duct entry K for the hood, in other words, the loss factor, that K factor for the hood is how much? Anybody remember? What was it? 0.7? 0.7, good. The elbow factor, now we got to go to our chart for elbows. That's 13. And we said, we didn't mention what the radius was, okay? The ratio of the diameter to the radius, right? So if the diameter of the ductwork, we may actually have to, let's start off by assuming it's 6-inch ductwork. Yes. Yes. That's the K value for the hood. No, the CE value is the efficiency of the hood. The K is the number that you multiply the velocity pressure to figure out how much of a loss you're getting going through a duct or going through a transition or going through an elbow or something like that. The Ks are always like a factor that's affected by the speed you're going through it. The CE is basically really kind of just an efficiency factor. Okay, so we're not really going to use that for much. So K for the hood, I'm going to say that we're going to design this, and no matter what size the diameter of the duct comes out, that we're going to work with something that's going to the ratio of the radius of the turn to the diameter of the ductwork is going to be 1.5, and it's a four-piece duct, a four-piece elbow, so the K factor is 0.27. Okay, so I'm going to put in here for the elbow 0.27. If I had two elbows, what would that be? Yeah, it would be 0.54. We just multiply it by 2. Good. Okay, now the branch entry. Okay, is there a branch entry involved here? No, right? Okay, is there a system effect factor? What is a system effect factor? A system effect factor is when something unusual is going on that's going to give you some extra turbulence. One example of that is when you have a elbow very close to the fan. So now you're combining the the special turbulence you got from the fan with the turbulence that's going on in that elbow, right? So the two of them combined give you more than you would expect in the way of a K factor from just that elbow. There's a chart in here on how to estimate what that is. You can avoid it in a lot of cases. How can you avoid it in a lot of cases? Don't put an elbow right next to the fan. In other words, your duct comes here, make a turn, make sure you got at least a length of 6 diameters before you go into the suction of the fan, and you won't have a significant system effect. Okay, so we're going to make sure of that, so we're going to put 0 for that. Okay, so now, where are we? Other Ks, we don't have any other Ks. Okay, another K would be if you had a K factor for a filter. If the manufacturer says this filter has a K value, a factor you use to calculate your resistance to airflow has a K factor of 2, or K factor of 1.8, or K factor of 3. He might instead give you a chart that says if the velocity air going through here is 1,000 feet per minute, figure 2 inches of static pressure loss. Or at 2,000 feet, figure 4 inches static pressure loss. He may give you a table like that where you know the static pressure loss. If that's the case, you would put it below in the next step, not here. Okay, if you know the K factor for the filter, you would put it there. Okay, there's no filter. We're going to a junction, there's no filter, so it's 0. Okay, so the total K factor is 2.07, partly from the acceleration factor, partly from the duct entry, and so on and so forth. Okay, so the static pressure what's the static pressure outside the hood is 0, right? There's no static, it's starting from plain air, dead air outside. So your starting static pressure is 0. There's no filter. If we had known the static, like here, they probably put in a 2 here because that might have been the static pressure introduced by the filter if the manufacturer had given you that instead of the K value. So the total static pressure is 0. Now, according to this, in order to get the velocity that we wanted, the 2,000 feet per minute, and get that Q value, we need a duct that is 8.6 inches in diameter. That's the ideal duct size. Can you go to Granger and order 8.6 inch diameter duct? They can't, so you got to choose 8 or 9 inches, right? So in this one, it put in 9 inches for us. The only problem with that now is our actual duct velocity, our transport velocity, is 1,800 instead of 2,000. Is that worrisome for us in this situation? What are we sucking in here? We're sucking in a vapor, right? So that vapor is going to move along no matter what we do anyway. So be honest with you, so we're a little under. I don't care. I'm going to stick with 9 inches, 9-inch duct, because it's going to be less resistance to flow. It's going to be a little bit easier. Had this been silica dust or something like that, which is big particles, and I really think it could drop out and build up in the ductwork, I might have said, oh, let's change this to 8, and it'll automatically adjust everything. And now the capture velocity is more than you need, but at least you know you're going to keep that stuff moving through the duct. But since it's just fumes, I'm going to stick with the 9. Okay, you guys agree with that judgment or disagree with that judgment? Seems reasonable, right? Okay, so now all the stuff that's in pink here is stuff that's being calculated by the program. So now what's the hood static pressure? It calculated it for you, 0.35. What's the static pressure at the junction? That's the 2, 0.69. Okay, so now we know all of these values for the what this branch is going to be doing in order to get us our 800 feet per minute, 800 cubic feet per minute, and our 2,000 feet per minute transport velocity. Okay, so now I'm going to do the second duct work, the second run of duct, the second hood. Okay, now the second hood goes from B to C. Let's remind ourselves what we got there. It's got a K value 1.78. We need to pull 250 cubic feet per minute of air through it in order for it to work. It's got 30 feet of duct work and 1 elbow on it. So let's go here and we'll tell it what it needs to know. First thing we got to do is start at the top. Are we coming from a hood, a junction, or a fan? We're coming from a hood. We're starting B. Remember, B is the other hood. We're starting from a hood. Agree? Right, Brittany? No. Now, you understand why I'm saying? Because we're starting at this hood. That's B. That's point B is a hood. And then we're going to join the junction up here. Okay? Okay, good. You're not filling me with confidence when you say it that way. Okay, so where are we going from the hood? We're going to the junction, the same junction as the other junction, right? It's the other side of that. Okay, so now we're gonna fill in what's gonna happen from B to C. What's our flow? What's Q that we need here? 250, right? What's our duct length? That was a 30? Okay. What's our target velocity? This one was higher, right? We wanted something higher for transport velocity. Did I write it down? I think it was 3,000 or something like that, right? Right, because it's a particle. It's I think we said it was if we call it a fine dust or powder. So that's 3,000 on the chart. Okay, 3,000. Yeah, I look at the chart, and on the chart it says, on chart 10 that you have over there, it says, well, I'm sorry, chart 9 rather. I go to chart 9, and it says I got mine mixed up here. For a fine dust or powder, you need 3,000 feet per minute. For very, very fine, very light dust, 2,000. For medium dust, 3,500. For coarse dust, heavy dust, 5,000. Okay, so what is our duct roughness factor? Galvanized iron? 1. Okay, well, no, there's no slot, so that stays 0. I'm sorry, there is a slot. Yep. Okay, so we got a slot. What's the length of the slot? 4 feet. Right? Remember, there's a slot. You remember there's a slot at the back of this hood. Right? See the slot back there? Okay. Don't worry about the 1 inch. Could be any size, but it's 4 feet wide. The length of the table, the width of the table is 4 feet, so it's 4 feet wide. So it wants to know the width of the length of the slot in feet. It wants to know the desired slot velocity. Seems to me when we were looking at chart 13, chart 11. Yeah, let's make it 1,500. Okay, desired slot velocity is 1,500. Okay, the acceleration factor. Whoops, I put an extra 0 there. The acceleration factor, what is that? If I'm coming from a hood, it's 1. No hood, it's 0. We're coming from a hood, so it's 1. Chart 11, duct entry factor from that hood. What was that? 1.78. We got that from our remember, that's because it has a tapered takeoff, right? If we're a straight takeoff, there'll be more turbulence and it's higher. Okay, what's the elbow factor? We're using the same kind of elbow, so the elbow factor, 4-piece elbow with a 1.5 radius to diameter ratio is 0.27. How many elbows we got? Just that one, right? It's only a single elbow, so that's 0.27. Yes. What's that? Oh, I considered that I included that up with, that's why I'm got that K, that 1.72, right? Like in other words, On this one, I was assuming that it's a straight run into the hood. You're right. I could have drawn, if I want to make it more complicated, I could have put another elbow in there showing it turning and going up. I hope your drawing will be more detailed than this and perhaps a little prettier than this. But you're right. You could put as many elbows as you want. I'm sorry. What's that? No, you're not going to copy what I'm doing. You're going to give me your own hoods. Okay, so, but I mean, in a sense, when you go back through this, you're going to be doing the same exercise, except you're going to be making your own decisions about how many elbows, what kind of elbow, and so on and so forth. Okay, so now, where was I? Acceleration factor is 1. The duct entry factor, K factor, is 1.78. That's from chart 11. We have 1 elbow. You guys might have 2 if it had 2. Let's put 2. Let's say you're right. Put in a second one. So we're gonna change that to 0.54. Okay? All right, happy now? Okay, now branch entry factor. Yeah, branch entry factor. What's the branch entry factor? Got another chart for that. Okay, if you look at chart 14, it shows you a typical branch entry. All of the losses are taken from the second hood that's joining the original branch, the main duct. Okay, so all of the losses are taken here. We don't put in a branch entry for the first hood. We put it in for the second hood. And what is it? Well, for a 30-degree angle, the K is 0.18. Had it been a 45-degree angle, it would have been 0.28. So in here, the branch entry loss factor is what did I say, 0.18? 0.18. Do you see where that came from on chart 14? Huh? Yeah. Okay, yeah. Well, the elbow was 1.5. I said 1.5 radius to diameter, like the ratio to radius to diameter, and it was a 4-piece. So you go across, and it's 0.27. Okay. Okay. System effects. System effects. No system effects. Other K values. Well, there's no filter. There's no other thing over here, so that's 0. Okay, the total K now is 3.6. That's because of like the very high K value for that. You remember when you have a slot hood, you're going out and you're like immediately going into some sort of taking from that slot. It's all collapsing together. It's very turbulent back there. So that's why that K is so large compared to that simple hood that we had before. Okay, so next, my static pressure from is 0 because it's starting from outside air. So the starting static pressure is 0. Okay, the only time static pressure wouldn't be 0 is when you're coming from a junction, right? Because it'll have a static pressure then. But we'll see that in a second. Okay, so other static pressure from other users like filters or whatever, or a static pressure drop from a filter or something like that. We'd fill in here. We don't have any. So the static pressure, some of the starting static pressures are 0. So it says the ideal duct diameter here is 3.9 inches. Why is it so small? Why is it so small? It's so small because we only need 250 cubic feet per minute, and we need to have 3,000 feet per minute velocity. So if we're going to get 250 feet per minute and we give it a big duct, it's going to be moving very slowly. So that duct has to be smaller and smaller and smaller until we reach that 3,000. So that winds up being a 4-inch duct. Okay, now 4 inches is a little bit bigger than that, but it's pretty damn close to 3,000, right? In other words, you have to make the choice here of what the actual duct diameter is. It tells you it should be 3.9 inches if you want exactly the right duct size. But you have to choose, is it going to be 3, which would give you 5,000 feet per minute, and a really big, look at the static pressure drop, 10 inches, 10 or 11 inches. But a 4-inch duct, okay, it's only 3-inch static pressure drop. And you're very close. Then you would add 5,000 feet per minute. Think about 5,000 feet per minute. This thing would be whistling and vibrating like a banshee. So we don't want to get ridiculous with this. So I'm going to use 4 inches for that. Okay, so it's calculated all this stuff for us. Okay, so the total Q value, the total amount of air that's moving through this thing is up to that point, through that point C, is 1,900 and almost 2,000 feet per minute. And the total static pressure, well, let's take a look at the static pressure. The static pressure that we calculated, let's see, where is it? The static pressure at 2 is 0.69 when we're coming from the first hood. And it's 3.31 when we're coming from the second hood. Oh, we got a problem. The problem is that they got to be closer than that, right? In other words, it's okay. If you look at the ratio of the static pressures, it's 0.21. It's got to be between 0.8 and 1.2. Because think about it. This is saying that it needs a static pressure of 0.35 to operate, to operate properly, coming from the first hood to that junction C. And this one needs almost 2 inches. They need a drastically different amount of static, 0.69 and 3 inches. That's drastically different static pressures at C. So you got to choose one or the other. But they're so far apart that we want them to be no more than 20% off from each other, right? So that we don't get weird system effects there. So now we got to figure a way to get this static pressure, this 3.5, this one down or the other one up. Well, how do we do that usually? By changing the size of the duct. Let's see what happens if I make this a 7-inch duct. Well, now this is up to 0.95. It's still kind of bad, right? Now, what about if I make this 6-inch duct? Okay, well, now my static pressure here is 4.26 inches. See it there? Static pressure at C is 4.26 inches. And my actual duct velocity is much higher than I really need, but those are the breaks. I got to satisfy this. I got to get these two static pressures to be the same. Now it's 4.26, and this is 3.31. What's the ratio? It's now 1.29. So if I go to 7 inches, that ratio is 0.64. So I have to pick one. I have to pick 6 or 7, one or the other. So let's see, 0.64 or 6. Yeah, remember what happened when I increased the other one? It went really crazy, right? So I don't think I want to do that. So I think the closest I'm going to get is to make this duct a 6-inch duct. Okay, and make this duct a 4-inch duct. So the total amount of air that I'm moving is, let me see if I still got, what's that? The real key here is they got to be close enough so that they're, remember that we, at point C, we need so much static pressure to make hood A work right. And we need so much static pressure to make B work right. But you can only have one static pressure there. So you got to have some sort of, by manipulating the size of the ductwork, you get that to the point where you try and get that to close as the same number, get the ratio as close to 1 as you can get it. So 1.29 looks about as good as we're going to get here. This is a really odd combination of ducts, the slot hood and this little tiny, it would have worked, would have been a lot easier to balance this thing if we had used a larger, like this had been a 1 foot by 3 foot, a rectangular flanged hood or something like that. Okay. And if this table, well, it doesn't matter. What's the difference? Okay, so the total Q that we need now is 1,084, and the static pressure at C, we want the governing static pressure is always going to be the highest of the two. So the static pressure at C, the total static pressure at the 2 point, the C, is going to be either 4.26 or 3.31. It's going to be 4.26. And if you look down here, it says the governing static pressure is 4.26 right there. Okay? And it's and the amount of air we're moving is 1,084 cubic feet per minute. Okay, so now it's that we're done with the two hoods and the two systems. So now we have to continue from point C. We're going to go from point C to point D. And what do we got there? We've got 50 feet of ductwork and a filter. Okay, so now let's go to point C. Yeah. Okay, and Let's see. And now the main duct is 6 inches and that branch duct is 4 inches now. Okay. Now we're going to go from C to the suction of the hood, which is we're going to call D. Okay, so I'm going to go down to the second spreadsheet. I'm going to start it. First of all, I'm going to fill this in. The quantity air moving through the main branch was, no, hang on a second. We changed it, right? Was 800, right? Here it is down here. Q, the corrected flow rate based on the changes that we made is 800 cubic feet per minute. Remember, we wanted it to be 800. Turns out that one came out just exactly there. So the corrected flow rate is 800 from the in the main duct, the main hood. From the branch duct, what was it from the branch duct? It was 284, adding up to 1,084. Whoops. Yeah, I'll get back there. 1,084. 284. Okay, what's the velocity pressure in the main duct? Okay, let's see. The main duct, the velocity pressure is up here somewhere. The the actual duct velocity pressure is 1.04 inches. Oops. Is 1.04 inches. And the velocity pressure in the branch, I saw it here, junction, duct velocity pressure, corrected velocity pressure, 1.04. Branch velocity pressure. Yeah, it could be. Hang on. Where do you see it there? 1 point, hang on a second here. Duct velocity pressure, 1 point, oh yeah, there it is. Yeah, there it is in the branch. It's 0.51. Right, because the air is moving at a different speed in that duct, so it's a different velocity pressure. 0.51. Okay. Okay, that's 0.51. Okay, let's go start here. Let's start from the start here. Okay, we're coming from now a junction, right? This run now is going to be C through D. Okay, D is the suction side of the fan. Okay, so we're coming from a junction and we're going to another junction or a fan. We're going to the fan. If we were going to a third hood, we're going to have a third hood join in. We would use this now to calculate for the third hood. Okay. Okay. Oh, are we okay? That's going to be a 1 because it's a fan. Okay. So now the desired flow rate. Let me see here. Okay. So the desired flow rate is going to be. Let me see here. Where am I? I'm on this one here from the fan. Okay. So the flow rate is going to be 1,000. What was it again? 84? Okay. And what's the duct length? How much was it? 50 feet. 50 feet to the filter. Another 50 feet. The target velocity. What's the target velocity we need now? Okay. Well, it's going to be the higher of the two, right? Because we got to keep that stuff moving, right? Which was 3,000. Right? 3,000 feet per minute was the target. It was the transport velocity. The roughness of the ductwork, that 50 feet of ductwork is 1 because it's galvanized iron. There's no slots, so those two are 0. Now the acceleration factor. This time we're not coming from a hood, so that's 0. The air is already moving, so that's 0. The duct entry from a hood. We don't have a hood there. The elbows. How many elbows are here? Any elbows? No elbows. Going straight into the fan. Okay. So the elbow losses are 0. Doesn't just go straight to the fan? We're going from C to D.
Yeah.
Oh, I'm sorry. You're absolutely right. Okay, so actually this is 70 feet and it's got 2 elbows in the filter. Okay, good. Yeah, you know what it was? I fooled myself here because I originally was going to make that the fan. And I put D over there. Really, D is over here, the suction of the fan. Right, D. Okay. Yeah, it's kind of a really oddball system that we drew here, right? Okay, so at any rate, try and stick to one kind of, one kind of media. Yeah, so at any rate, so from C to D, we go 70 feet, not 50, 70 feet. No slot. The acceleration factor is 0 because we're not coming from a hood. The elbow K factors. Now we have 2 elbows, right? Those 2 elbows are going to make this how much? 0.54. Okay. And our branch entry effect. Okay. We're not going into a branch, so we're not going to use that. System effect. We're not going to use that because presumably we're going to run into that. We're going to have at least 6 diameters before we connect to the fan. Oh, we're going to get to that. Okay, so now other K. The filter manufacturer is either going to give you a K factor or he's going to give you a static pressure drop, right? If he gives you a K factor, you put it in there. Let's say for our purposes that this thing with the media and the activated charcoal combined has a K factor of 2. We would put it there, okay? So had he given us the static pressure, we would have put it here at static pressure. The static pressure from is how much? You guys remember what the static pressure was? The governing static pressure was before? Was it 4.26? Do I need to go back up there to check, make sure you're right? Okay, 4.26. So the static pressure from is 4.26. Okay, and if he had given us a static pressure instead of a K for the filter, we would have put it in here. Like, let's say if he said it was a 3 psi, 3 inches of water pressure drop, we would have put it in there. But he gave us a K factor, so it's already accounted for. Okay, so you're either going to account for the filter in here and the other static pressure drop, or by putting a K factor, like a loss factor, for the filter in there, depending on what you get from the manufacturer. Okay? Okay, so now ideal duct diameter size is 8.1 inches. We happy with that? Let's put 8 inches in there. And we get, there's our duct velocity. We got our 3,000 feet per minute. Okay, so we're in good shape. You're almost always, as long as what you put in here is a little bit lower than that, you're always going to have the velocity that you need. So we've calculated everything we need. Now, what's the static pressure? The static pressure at the 2 point, now this is the suction of the fan, is 7.1 inches, right? Now that the 2 is the suction side of our fan, that's 7.1 inches is our total static pressure at the fan now. Okay, so now we have to complete this. We're at the fan, we have to go up the stack. So the next row is where we take care of that. So we're coming from, what are we coming from? A hood, a junction, or a fan? We're coming from the fan, so we put a 3 in there. Where are we going to? We're going to a stack outlet or a junction? We're going to a stack outlet, 1. Okay, so this is going to be, just to make this neat, it's going to be D to E.
So your fan is right where I put D.
Yeah, right where I put D is the fan. Yeah, not this D, the one that I drew over here. It's right. There's the fan right here. These 2 are elbows, and then it goes right into the fan. Okay, so our desired flow rate, still the same, 1,084. Once you get your flow rate through this thing, you want that quantity of air is going to go. In other words, the only reason there's different flow rates was because we had one hood with one flow rate, another hood with another. But once they join into a single duct, all the way through that, it's got to be the same flow rate. You can't have air disappearing or being created in there. It's always going to be the same flow rate. Okay, so the duct length we have here, well, we said that's going to be a 10 foot. Why don't we make it 12 feet tall? Let's make it 10 since that's what's on the drawing. Okay, what's that?
If your fan is on the second thing, how will you
It's going straight up. See it there going straight up? In other words, the fan is over here. Here's our fan, whoops. Here's our fan right, whoops. Here's our fan right here. It's going into the fan, and then it's discharging straight up from the fan 10 feet to go outside of the roof. This is the junction. This is the duct that's going through the filter. It's making a left turn, a right turn, going into the suction side of the fan, and then the fan is blowing it up straight through the building. So the third column that we did on the spreadsheet was from C to D. Okay, and then that extra 10 feet is the discharge. So now we're doing D to E. D and E is outside the building. Okay, so let's yes. What's that? Oh my goodness. Okay, yeah, I got it here somewhere. Good catch. Did it go there yet? Not yet. Good. All right, we're getting like Flint now. Okay, so at any rate, so what's so the duct length is 10 feet. Okay, it could be more if we had to go a bigger distance to go to make it higher. Our target velocity. What's our target velocity? I'm going to say it's still 3,000 feet, 3,000 feet per minute. Okay, what's our duct roughness? Galvanized iron still, so it's going to be 1, no slot. Our acceleration factor, we're not coming from a hood, so no acceleration factor. Duct entry, no. Is there an elbow? No, it's coming straight out. Branch entry, no. System effect, no, because we're going to make sure that we give it enough distance before we go into the suction of the fan. Other K, any other Ks? No. Okay. Static pressure from, what's our static pressure at the start of this run? Right? Well, it's what the fan static pressure was, which was 7.1 inches. Our static pressure at the point D, which is the fan suction, was 7.1 inches. And any other static pressure losses? No. And the total sum of the static pressures on that side is 7.1. The ideal duct diameter for the discharge to get 3,000 feet per minute is not surprisingly the same as it was before, because same quantity of air. So we're going to make the stack 8 inches. And we find that when we go through this whole thing, we need a fan that'll give us the total fan the fan total pressure is 14 inches of water, and we're going to need a fan that delivers 2.5 horsepower of actual work, but we're going to need a motor of 6.3 horsepower. Why is that? Why does a motor horsepower have to be so much more than the actual work that we're doing? For a couple of reasons. One is that the mechanical efficiency that we're going to assume for this fan and motor is only 60%, and we want at least a safety factor of 1.33, 1 1/3. So that works out to we actually need a fan motor of 6.3 horsepower. That's not that big, really. Okay. So now, what could I do to cut down on that? Well, maybe if I made the stack duct 10 inches instead of 8 inches, I'm only going to get 2,000 feet per minute, but I'm already on the past the filter. What does that mean? That means I really don't have the particulate anymore. I can afford for the stack pressure to be lower because I don't have to transport those particles. So I'm going to make it a 10-inch duct stack instead of an 8-inch, and look how much smaller of well, not that much more. Let's try 12-inch. Let's try 12-inch. Okay, how about 12-inch? Well, nah, it's not affecting it that much. Still gonna need a bit of a fan. I'm gonna still need a bit of a fan to do that. I don't know. Let's give it a try. Well, this is not that bad, really. I mean, this is an industrial ventilation system, so not that surprising that you have a few horsepower fan. Okay, so that's it. We're done. We just designed the whole hood system, which we have we've determined. We know We know what the static pressure at this junction is. We know what size this duct has to be and this duct has to be in order for this to pull the air that it needs to and this to pull the air that it needs to. In other words, this design is self-balancing. We don't need any dampers in this because of the way we chose the duct sizes based on the spreadsheet and the way we're going to achieve the flow rates we want and the velocities we want through all of this duct work and the capture velocities at the distances we want it from the hood. All that's going to be achieved by the way we chose these various duct sizes and these junctions and so on and so forth. And we're going to filter the air. We're going to account for the losses due to the filter. We're going to count the losses for all the duct work and the elbows and so on and so forth. And we're going to size the fan. We have the specs that we need to size the fan appropriately to make this whole thing work. So we know what the static pressure is here. We know what the velocity and the amounts of air that are getting moved through here. We know what the velocity, the capture velocities are here. The capture velocities are here. We know, and so on and so forth. So we're in pretty good shape, right? We know all the parameters that we need for this hood, right? So now, if you went home and chose 2 different hoods, you would be able to do this, right? Don't you think? Yes.
So I know for like the air filter, you can look up like what the actual loss factor is.
Yeah, you want to know? You could try and Google. You could try and Google.
Well, I'm sure we can find it, but then my question is, when we get to the fan, we have to look up like.
The fans. Okay, we have a chapter in the book on the fans, and that chapter in book on the fans.
Say that we need a fan that would be good for the Jackson have to make sure we do.
Yes. Yep.
That makes it. I mean, I know it doesn't have to be exactly.
Yeah.
perfect,
Well, you know,
but-
I for your design, if you really, depending on, in other words, how much effort and detail you put into this, it's going to affect your grade somewhat. But if you calculated the basics, I want to see for sure is that you can calculate from these spreadsheets what the fan total pressure has to be and what the fan horsepower has to be, what the motor horsepower has to be. Of course, from that, you can specify that, in other words, when you go to the manufacturer's fan curve, that'll give you the information that you need to specify what fan you want.